This is part 2 of lesson 6 of unit 8, volumes by disk and washer methods. And in this section, we are going to look at the washer method. In part 1, we did the disk method. So in this part, we're going to do the washer method. So sometimes a cross section or a slice will create a washer. And this happens when you have two functions and you're rotating them together. So what will happen is you'll create a hole in your graph. So you create a disk. So most a washer. Most washers have holes in them. So it looks like a ring. So what you need to do is really you're going to take the volume of a larger cylinder and bore a hole out of it, which is the volume of the smaller cylinder. So each one of these is a little tiny ring that you're creating. So that's what we're going to be doing. So that's where this area formula comes from here. You're going to take the area of the larger ring and subtract off of it the area of the smaller ring, and that'll leave this hole here. And then you're going to multiply that by pi because it's a circle. And of course, if we're going to do the volume then, each one of these little rings here have a width to them that is dx wide. So then we have an area of a circle times a width of dx, and we create a ring of that respect. So our large R of x is going to be our outer radius. And in this picture, it's going to be f of x. And the inner radius is going to be little r. Oops, I forgot the word inner. And in the picture we have here, that's going to be G. And what it will create is a picture like you see in the third one. And what I want to do is I want to show you this graphic that I found online. And it is by mathDemos.org. And they do the rotation around the x-axis and then around the y-axis. So this is really nice. So what it's going to show you is how it creates a little wedge, rotating it halfway around the x-axis, each wedge, and you can see how they'll have a hole in them because you're finding the difference between those two discs. And so then the hole will come out, and you'll see the hole gets bigger the smaller it is because the two functions get further apart from each other. And so we create this beautiful picture here. Now, if you're rotating it around the y-axis, something similar, so we're going to rotate, let's do the first one, which is bounded by the graph sine of x. And so the sine of x, one curve of it looks like that, the purple part. And then we're creating those discs, and we're rotating them. And we have a little disc and a big disc, and so we're cutting out the little disc. So we're just left with a ring like that. That's one half of it. And then when we fill it in, we'll see that we just stack those rings right on top of each other, and we create our solid of revolution like that. Okay, so that's a visual of what we're doing here. Okay, so again, like with our disk method, define the volume of a solid of revolution where each slice of the region is to be rotated perpendicular to the axis of revolution. We use these formulas. And so if we are horizontally rotating it, which is around the x-axis, we're going to solve for y in terms of x, and so our width is going to be that dx. And you can see here is the larger area minus the smaller area times pi. And then if we were doing it around in the vertical axis, the y-axis, we now need to solve for x in terms of y. So our width now is that little dy. All right, so let's do some examples. Example 6 says, find the volume of a solid generated when the region between the graphs of f of x equals 1/2 x squared and g of x equals x over 0 to 2 is rotated about the x-axis. So we have this line, for y equals x, right here. And then we also have our parabola that is at 1/2, and it is going to look something like this. And then we have this region in between them here. And we are rotating this between 0 and x equals 2, right here. Here's our 2, here's our 0. So we have two r's. Here's our little r, and here is our big R. So big R is going to be 1/2 x squared, and little r is going to be x. So our volume is going to be pi times the integral from 0 to 2 of our big R squared minus our little r squared dx. So v is going to equal pi times the integral from 0 to 2 of 1/2 plus x squared, we're going to square that, minus x squared, this whole thing is dx. So when we expand this, we get v equals pi times the integral from 0 to 2. Expand and put everything together, we get 1/4. It doesn't look like a 4 very much. 1/4 plus x to the 4th, because the x squareds will cancel. And then this will be dx. So we get pi times 1/4 x plus 1/5 x to the 5th. And we're evaluating between 0 and 2. So our volume is going to be pi times 1/2 plus 32 over 5. So that's going to be 69 pi over 5. Okay, next example. Find the volume of a solid formed by the region bounded by the graphs of y equals the square root of x and y equals x squared about the y-axis. Okay, so we have y equals the square root of x, looks like this. Oops, I forgot to hit my little finger. And the graph y equals x squared looks like this. And so we're doing the region in between them, which is here. Okay, so now our r's are going to be taken horizontally. So big R is going to be furthest away from our axis of rotation, so that's to there. So that's big R. And our small r is going to be the closer one, right to here. So there's little r. So big R is going to be our x squared graph, but we want to solve this for x. So we're going to change this to the square root of y. And our little r graph is the square root of x, and we want to change that to be in terms of y, so we'll square both sides, so we get y squared. Okay, so now our volume is going to be the integral. Oh, we need one more thing, where they intersect. We know they intersect at 0, 0, and the other place these two are equal to each other. So where does x squared equal x in the first quadrant? I'm sorry, x squared equal the square root of x. That would be at x equals 1. So that's going to be the other point right here. So that's at 1. So we're going to do the integral from 0 to 1, and we need our pi out here. And we're going to have the square root of y squared minus y squared squared. This is dy. So we get v equals pi times the integral from 0 to 1. That's supposed to be a 0. It doesn't look like one. 0 to 1 of y minus y to the fourth dy. So v is going to equal pi times 1/2 y squared minus 1/5 y to the fifth, evaluated between 0 and 1. So we're going to get pi times 1/2 minus 1/5. So simplifying that, we get v equals 3 pi over 10. Okay, so now we're going to be using our calculator. Find the volume of the solid generated by rotating the region bounded by y equals x minus 1 squared plus 2, y equals x, and x equals 0 about the x-axis. So the picture's already drawn for us here, and we're doing about the x-axis, so we can see the closer r here. This is going to be our small r right there, that's r, and our large R, capital R, is right there. Okay, so that graph is going to be the parabola, which is x minus 1 squared plus 2, and our little r is just going to be x. And you can see we're rotating it 2, we get to 2, so here's 2. So the first thing we're supposed to do is write the area of a single slice. So the area is going to be pi times my larger r, which is going to be x minus 1 squared plus 2. And we're going to square that. And then minus our x squared. So that is our area. And now we're going to write the integral for the volume. So the volume is going to equal the integral. We're going to put the pi out front there, from 0 to 2 of x minus 1 squared plus 2 squared minus x squared dx, because now we need a height of our disk. And then find the volume to 3 places. I just put this in my calculator because this is a calculator problem. So v is approximately equal to 21.677. Okay, finally, our last question. So now we have a solid plastic sphere of radius 5 inches. It's going to have a hole bored out of the center with a radius of 3 inches. So we have a 3-inch hole now. What is the volume of the resulting plastic sphere? Okay, so just showing a cross section of this. So now this is going to be sitting up here at 3, because there's going to be a hole, and there's going to be a bottom half as well. So it's going to sit up like this. So this is 3 inches here. This is my 3 inches right here. And the radius for this sphere is, it was 5, but so out here we're at 5. But now, if we look at the equation, we're going to have, of the cross section, we're going to have x squared plus y squared equals 25. So we're going to have y equals the square root of 25 minus x squared. We're going to need that. To find the interval now, we know we need these values here at either end. And it's not going to be 5 and negative 5. What's going to happen here now is we have a y value already. We know the y values are 3 at both ends. So in our equation, x squared plus 3 squared has to equal 25. So what x values give us that? So we're going to get x squared equals 16. So my interval is going to be plus or minus 4. So it's going to be from negative 4 to 4. And then my integral is going to be v equals pi times the integral from negative 4 to 4 of, and now I have this huge thing here.
Your attention, please.
So this is going to be the square root of 25 minus x squared minus this radius of 3 inches, so that'll be 9 dx. And again, this is a calculator problem. So this is going to be approximately equal to 268.084 3. And that concludes our lesson on the washer and disk method.